Okay, so acidizing, right. You hear that and it sounds like some kind of like harsh industrial cleaning thing.
Yeah, it kind of does.
But sandstone matrix acidizing, this is different. This is delicate. This is about restoring flow in a well by clearing out these teeny tiny blockages in the rock pores.
Exactly.
And like right off the bat, we got to make it clear this is not the same as acidizing carbonate formations.
Right, right. Totally different ballgame. With carbonates, you're actually dissolving the rock itself to make those flow paths.
Yeah, like replumbing, right.
Exactly.
Yeah.
But with sandstone,
Yeah.
much more delicate, more like carefully cleaning out those existing pipes.
Yeah.
And
Yeah.
sandstone, well, it's got this like way more complex mix of minerals.
A whole mineral cocktail down there.
Yeah, it really is.
Yeah.
So yeah, the chemistry gets a lot more intricate, a lot more to think about.
And you aim for what, like a 75% success rate on these treatments? That shows you just how much the chemistry matters.
For sure. You got to know what you're doing down there.
So you've shared some like seriously in-depth stuff with us on sandstone acidizing. And what we're going to do is pull out the most crucial bits of knowledge for you. Think of it like we're going through research papers, articles, even your own notes from out in the field
Yeah, I love that.
to bring you that core understanding. So our mission today is simple. Give you a clear picture of the chemistry involved and all those factors that make a sandstone acidizing job successful without drowning you in details. Okay, so first things first. What exactly is sandstone in terms of treating a well?
Well, when we geologists and petroleum engineers talk about sandstone, we're mainly talking about rock with a lot of quartz,
Yeah.
Silica.
Right.
But it's almost never just pure quartz down there. Your sources point out that you also get all sorts of other minerals mixed in: aluminosilicates, metallic oxides, sulfates, chlorides, carbonates, even some amorphous silica, the non-crystalline kind.
Like a geological melting pot.
Uh-huh. Yeah, you could say that.
Now, there's this term, detrital species. What are those in this context?
Basically, they're the minerals that were deposited way back when, along with the original sediment, the stuff that eventually formed the sandstone.
Okay.
And here's the interesting part. These minerals often have water associated with them.
Mm-hmm.
So as we start producing oil and gas, the movement of those fluids, it can actually dislodge some of these fine detrital particles.
Uh-huh.
And then these tiny particles, they get caught in the narrow spaces between the pores in the rock, blocking them up. It's kind of like, imagine shaking a jar full of sand, and the smallest grains settle and plug up the gaps.
Yeah, makes sense. Now, the material also talks about connate water and authigenic species. What's the difference there?
Right, so connate water is the water that's naturally trapped within the sandstone itself. Usually has some dissolved minerals in it. But the wild thing is, when we start producing and the pressure drops down a hole, it messes with that delicate balance in the water.
Oh, I see.
And that causes some of those dissolved minerals to precipitate out. They form what we call authigenic species. So think mineral scales, like calcium carbonate, but also some clay types. Zeolites, elites, kaolinites, smectites, these basically grow in those pore spaces over time. So we're trying to get the good stuff out, but we can actually end up making more blockages.
It's like the well's fighting back.
In a way, it is. And that means we're not just dealing with static rock here. It's a dynamic system, always changing.
Right, and that's where the whole idea of formation damage gets really interesting, because the material talks about damage that actually comes from our own well operations.
Yeah, that's a huge factor. When we drill and complete a well, we introduce all kinds of stuff into the formation.
Like what?
Drilling mud filtrate, completion fluids, they create whole new chemical environments. And those can cause just as much trouble as the natural stuff. Plus, you get damage during perforating, gravel packing, even just from regular production or injection over time.
So you're saying even just using the well causes problems?
Exactly. It's a constant battle.
Yeah.
And this is why, to pick the right type and strength of acid for treatment, you absolutely have to understand the chemistry.
Of both the rock itself and what's causing the damage.
Both, yeah.
Yeah.
You can't treat one without knowing the other.
Which leads us to the big gun, hydrofluoric acid, HF. It's described as the main solvent for sandstone. And then you've got those mud acids, which are mixes of HF and hydrochloric acid, HCl. Why that combo?
Well, initially, those mud acid mixes were for dealing with, well, mud damage. Makes sense, right?
Yeah.
But over time, it became clear that this combo was effective against a lot more types of damage in sandstone. Now, we might have talked about HCl reactions before, but they're definitely relevant here. Because remember, sandstone isn't just silica.
Right, the mineral cocktail.
Exactly. So HCl can play a role in dissolving some of those components too.
So, talking about the fluids used, the source material emphasizes this dual compatibility for HF blends. What does that mean practically for someone actually doing the treatment?
It means that whatever you're using, any blend with HF in it, it's got to be compatible with two things: the original minerals in the sandstone and the stuff causing the damage.
Two targets at once.
It's a balancing act for
Mhm.
sure. And that's where the HCl pre-flush comes in. Injecting hydrochloric acid before the HF mix, almost always a must-do.
Why is that so important?
It prevents certain reaction products from the HFs from precipitating out. Those products, they're less soluble. They can cause even more blockages if we're not careful. Think of it like we're trying to dissolve the problem, but we can create a new one if we're not controlling the chemistry precisely.
Like, specifically, the material says there's a risk of calcium fluoride forming if HF hits calcium carbonate directly. And that's the opposite of what you want, right?
Yeah, exactly. If you're trying to increase flow, you don't want more solids forming.
So the HCl is like clearing the way for the HF.
In a way, yeah. And the thing is, HCl with carbonates, that's pretty straightforward. But HF with silica minerals, that gets a lot more complex. And it's not just carbonates you got to think about. There's this whole group of minerals, zeolites. They're particularly sensitive to hydrochloric acid.
Zeolites, they're described as crystalline but also hydrated with these like porous channels, like natural sieves almost. Where do those come from?
They often form in areas with volcanic activity in the past, or they can come out of silica-rich water and downhole under all that pressure and heat. They can change, morph into different but related minerals. There's even a table in your sources that shows this.
Oh, wow.
But the main thing to remember is zeolites are always authigenic, meaning they form within those existing pore spaces in the rock.
So they're just hanging out in the pores and then HCl comes along and can cause damage. The material even mentions studies where they saw this in core samples. But then it says weaker organic acids might not fully restore permeability. So what do you do if you think there might be zeolites in a formation?
You got to recognize that possibility before you even think about the main acid treatment. That's step one. And the way to handle it is usually a two-part approach. First, you use an organic acid as a pre-flush, one of the first things you pump down. Then you go in with a low-concentration HF mix, specifically targeted at the other minerals.
So gentler at first, then more targeted.
Exactly. And another important point is all the fluids should have some organic acid in them. That helps keep the pH low, which is important for preventing unwanted reactions. In really hot wells, some people even go with an all-organic pre-flush first, then the organic HF blend. It's all about controlling the chemistry.
Makes sense. Now let's get down to the details of hydrofluoric acid itself, the chemistry, the reactions.
Right, let's dive in.
It's described as basically the only common and affordable acid that can actually dissolve those silica-based minerals.
Pretty much, yeah. If you need to dissolve silica, HF is your go-to.
So how do they actually formulate it for use in wells?
Couple of common ways. One is dissolving ammonium bifluoride in HCl. Another is just diluting concentrated mixes of HCl and HF. And that ratio, HCl to HF, that's super important. It gets adjusted based on what minerals you expect to find, how much you think there is, and you can fine-tune it even more with those pre- and overflushes we talked about.
It's like a recipe almost.
Kinda, yeah. You're tweaking the ingredients based on what you're cooking up down there.
Now, we know HF reacts with a whole bunch of different minerals, usually forming these aluminum silica fluoride complexes. And these reactions, they've been studied for decades, right?
Oh yeah, long history there. Lots of research trying to understand exactly how it all works.
So that HCl pre-flush, it's not just a good idea, it's essential.
Absolutely essential because, like we said, it prevents those insoluble precipitates. Things like calcium fluoride, which happens if any carbonate's left over, and those sodium or potassium hexafluosilicates, which happen if the HF gets to the formation brine too early.
So it's like a protective barrier, almost.
That's a good way to think about it.
Yeah.
Now, we've touched on the HCl carbonate reactions before, so let's focus on how HF tackles those silica-based minerals.
All right, so chemically speaking, HF is a weak acid. Doesn't fully break apart in water.
Right.
And at those high concentrations, like in the ultramud acid, it can even form those HF2 complexes.
Yep, gets even more complex then.
But when it reacts with pure silica, like quartz, it's a two-step process, right? First, you get silicon tetrafluoride, CIF4, and then silicon hexafluoride, CIF6-2.
Correct. And usually the CIF4 stays dissolved under the pressure downhole. But some of it can react with water. Hydrolysis is called. And that forms monosilicic acid and actually releases heat as it does it. And if
Mm.
there's enough silicon in the water, you can even get fluorosilicic acid, H2SO6.
So even with just silica, it's multi-step, it's got byproducts, it's got heat.
It's not simple, that's for sure.
And then when you add in the aluminosilicates, the feldspars, the clays, those have both aluminum and silicon.
Yeah, then it gets really fun.
So how does that change their reactions?
Well, for those aluminosilicates, the breakdown by HF, we often consider it stoichiometric. Like a recipe, right? For every bit of mineral that dissolves, you get a specific ratio of aluminum and silicon released, matching the ratio in the mineral itself.
It's like a balanced equation.
Yeah, exactly. Now, silicon, it kind of follows a similar path to what we talked about with quartz. But aluminum, that's where it gets interesting. Aluminum can form a bunch of different aluminum fluoride complexes, and which one is dominant? It depends on how much free fluoride ion is around at that moment.
So as the HF reacts as it gets used up, the dominant aluminum complex can change.
That's right. It's dynamic, always shifting.
And it's not just aluminum and silicon, right? The material mentions other metal ions like sodium, potassium, magnesium, calcium, iron. They get released too.
They do. They become free ions in the solution. And iron, specifically, from iron-rich minerals, it can form its own set of iron fluoride complexes. The material even gives some examples. The reactions for kaolinite and feldspar gets pretty detailed.
Shows you just how much is going on down there. But dissolving the minerals, that's just the first part, isn't it?
Yeah, that's just the beginning.
What about all the byproducts, all the stuff that's left behind?
That's crucial, and it's where things can go wrong. When you dissolve minerals in HF, you create all these byproducts. And the problem is, many of them can precipitate out under certain conditions.
Like they become solids again.
Exactly. And that can clog up the pores, defeating the whole purpose.
So you're creating a new blockage while trying to fix the old one.
It's a real risk.
Yeah.
Your sources even have a table listing some of these potential precipitates. And one of the main drivers for this is the pH of the solution. As the acid gets used up, as it spends, the pH goes up. And that can trigger precipitation.
So the more the acid works, the more likely it is to cause new problems. That seems counterintuitive.
It's a delicate balance, for sure. Ideally, you want to limit precipitation as much as possible. And if it does happen, you want to dilute it, push it away from the wellbore. Now, boric acid, that can help redissolve some of the calcium and sodium precipitates. But potassium precipitates, and some magnesium ones, they're tougher. They don't dissolve as easily. That's a headache we got to watch out for.
And then there's colloidal silica precipitation. The material says that fluorine is more attracted to aluminum than silicon, and that can speed up the breakdown of those silicon hexafluoride complexes, leading to this, like, gel-like silica forming. But there seems to be debate about how bad that really is.
Yeah, that's a real discussion in the industry. Some people, they're convinced that colloidal silica is a major plugging issue. Others say that what looks like precipitation is actually a topochemical reaction, meaning it's a surface change on the clay, where fluoride swaps places with aluminum. And they argue that might not cause much damage to flow.
So, two different interpretations of the same phenomenon.
Yeah, and we don't have a definitive answer yet. What we do know is that higher temperatures downhole make it worse. And certain clays, montmorillonite especially, they accelerate it too. In some cases, you can even see the aluminum totally stripped from the clay, with silica left in its place.
Wow. So some specific precipitates to watch out for. Calcium fluoride, KF2, seems like a big one, especially if there's any calcite, the calcium carbonate around.
Oh yeah, CAF2 is trouble. Even a little bit of carbonate left over after the pre-flush, or just carbonate coatings on other minerals, that's enough. It reacts super easily with HF, forms that calcium fluoride, and that stuff, it can really clog you up. Now, there's a slight chance it might redissolve later on, when the HF is almost spent and there's more aluminum around, but don't count on it.
So hope for the best, prepare for the worst.
Exactly. Then you've got the alkali fluosilicates and fluoilluminates. Those are a real pain.
What makes them so bad?
They form when those aluminum or silicon fluoride complexes react with alkali ions, sodium, potassium mostly. And where do those ions come from? The breakdown of certain clays and feldspars. Now, if you've got high HF concentrations, that makes precipitation more likely. And these precipitates, like sodium fluosilicate, potassium fluosilicate, they're well-formed crystals. They can really cause some serious, long-lasting damage to permeability.
So another reason that HCl pre-flush is so vital.
Huge reason. Got to get those alkali ions out of the way before the HF gets there.
Okay, what about aluminum fluoride, LF3, and aluminum hydroxide, LOH3? Those can form too, right?
They can, usually as the acid spins. Now, for LF3, Keeping a high HCl to HF ratio helps. As for iron precipitates, if there's a lot of clay, you're probably less likely to see iron fluoride complexes. Aluminum grabs those fluoride ions more readily, but iron hydroxide, that can form if the pH goes above about 2.2. And if you've got dissolved iron and a bunch of calcite, well, then you can even get ferrocarbonates forming. Not good.
So many ways for things to go wrong.
It's a complex system, for sure. But understanding the chemistry is half the battle. Then we got to think about the speed of those reactions, the kinetics.
Right, because the material says that sandstone acidizing is often kinetically controlled. What does that mean, practically speaking?
It means that the overall speed of the treatment, how fast it works, it's mainly determined by how fast those reactions happen at the mineral surface, not by how fast the acid moves through the pores.
Okay.
And there are several factors that can affect those reaction rates. The concentration of HF itself is a big one. For most minerals, except smectite clay, the faster the dissolution, the higher the HF concentration. So in weaker formations, or ones with a lot of fine particles that could move, you might want to use a lower HF concentration, maybe around 1.5%, especially at higher temperatures.
Why lower concentration at higher temperatures?
Because you don't want the acid working too fast. You could end up dissolving the rock matrix too much, making it crumble. Fluoboric acid, which we'll talk about later, it's similar. It keeps the free HF concentration low, which can be a good thing in certain situations.
Makes sense. What about the HCl concentration? It's there to prevent precipitation, but does it affect the reaction rate too?
It does. Generally, higher HCl means faster dissolution. The idea is that the hydrogen ions from the HCl, they can interact with the mineral surface, making it easier for the HF to attack. But the exact relationship can be pretty complex, depends on the specific mineral. The material even gives some equations for how quartz and feldspar dissolve. It gets pretty mathy.
Oh boy.
But the key takeaway is that HCl plays a role in the speed of the reactions, not just preventing side reactions.
Then there's temperature.
Yeah, temperature's huge. Heat speeds up pretty much all chemical reactions, so the hotter it is downhole, the faster those minerals dissolve. The material mentions activation energies, which basically tell you how sensitive the reaction is to temperature. There's even a chart showing how mud acid reacts with silica glass at different temperatures and HF concentrations. And just as a side note, aluminum and iron, they also become a bit more soluble at higher temperatures.
So many variables to consider. And then there's the actual rock itself, right? What it's made of, how much surface area there is for the acid to react with.
Yeah, that matters too. Sandstone, because it's made up of all these little grains, it's got a lot of surface area inside those pores. And that's what really drives how fast the mud acid gets used up, how fast it spends. But different minerals react at different speeds. Clays are the fastest, then feldspars, then quartz, especially when you've got a lot of those hydrogen ions from the HCl around.
So even if quartz is most of the rock, it might not be what the acid spends on the most.
Exactly. You'd have a tiny amount of clay that reacts way faster than all that heritage. So again, having enough HCl in both the pre-flush and the main mix, that's crucial for dealing with those fast-reacting minerals.
And one last thing, pressure. Does that make a
Yeah.
difference?
It can, a little bit. Higher pressure can speed up the dissolution, especially for quartz. We think it's because some of that CIF4 we talked about, it gets converted into fluosilicic acid, which then reacts further. There was one study that showed under extreme pressure changes, the reaction rate for quartz went up by almost 25%. But it's not just the pressure itself. The shape of those pores, how the acid actually flows through them, that matters too. The acid often prefers the bigger pores, so that affects how it reacts with the rock.
So all these factors, the acid, the temperature, the rock itself, the pressure, how do they predict what's going to happen down there? How do they model these reactions?
That's where the clever people come in. They build mathematical models. They try to take all these factors, put them together, and predict how the formation will change as the acid goes in. And to simplify things, they often treat sandstone as a two-component system. One component that reacts slowly, usually quartz, and another that reacts fast, representing everything else.
So like a simplified version of reality.
Yeah, you got to make some assumptions to make the math work. But these models can be pretty good.
And the material says that the rate of these reactions in sandstone, it's usually limited by what's happening at the mineral surface itself. It's not like limestone acidizing, where it's more about how fast the acid gets to the rock.
Right. In sandstone, it's surface reaction limited, which means the permeability increase you get, it mainly comes from removing the existing damage, not from actually making the pores bigger. The HFs kind of dissolve stuff evenly rather than creating those channels, those wormholes you see in carbonate acidizing. The flow is more stable in sandstone, with pretty clear fronts moving out as each mineral dissolves.
It's a slower, more controlled process.
Yeah, you could say that.
Now, some researchers have tried to model this whole process. They use some pretty complex math. What can those models actually tell you, practically speaking?
They can predict a few things, like how far those dissolution fronts move, how deep into the formation the acid is actually reacting. They can also estimate how much of those fast-reacting minerals, like clays, are left as the treatment goes on. And based on all that, they can try to estimate how much the permeability will increase. They use terms like acid capacity number and dam-Kohler number to describe those processes.
Well,
But the general takeaway from these models, unless you use ridiculous amounts of acid, the HF tends to be spent pretty close to the wellbore.
so the penetration depth is limited,
It is, yeah.
which brings us to the idea that maybe regular mud acid isn't always the best choice. It's got some drawbacks. It reacts quickly, so it doesn't go deep. It can create fines that then clog things up, and sometimes it can even damage the rock itself.
Yeah, it's not perfect, that's for sure.
So what are some of the other acid systems they've come up with to try and improve on mud acid?
Well, there's a bunch. One that's gotten pretty popular is fluboric acid.
Right.
Now, fluboric acid, it's different. It doesn't have a lot of free HF at any one time. Instead, it kind of generates more HF as the existing HF reacts and gets used up.
So it's like a slow release of HF.
Exactly. More controlled, less aggressive. But the total dissolving power, that can be comparable to a weak mud acid.
And the material mentions it's got some specific uses, like using it as a pre-flush to stop those fines from moving, or even as the main treatment in some cases.
Yep, it's versatile. One thing it's really good for is formations with potassium-rich minerals. Because unlike mud acid, it doesn't tend to form those nasty potassium precipitates. It's also great for stabilizing clays and fines, stopping them from migrating and blocking stuff up.
So less damaging, and it actually helps prevent future damage, too.
That's the idea. Now, just a quick side note, in the field, they usually make fluboboric acid by mixing boric acid, ammonium bifluoride, and HCl. That sets off a bunch of reactions, and you end up with fluboric acid and the HF. But the chemistry is such that the free HF concentration stays pretty low.
It's like controlled chemistry.
You got it.
And they say it's actually a strong acid, like comparable to HCl in strength. But how does its dissolving power actually stack up against mud acid?
Well, in lab tests, they've seen that it reacts slower with things like silica glass than mud acid with the same total amount of HF. And this is important. It tends to cause less damage to the rock itself. So after treatment, the rock is often stronger than if you'd use mud acid. That's a big win.
So gentler on the formation.
Much gentler.
But the real advantage of fluoboric acid seems to be that clay stabilization. How does it actually do that?
The borate and fluoride ions, we think they react with the clays in the formation. This can make swelling clays less likely to swell, which is huge. And it can also reduce their cation exchange capacity. But this stabilization, it takes time. You often need a shut-in period after injecting the acid to let those reactions happen. And during that shut-in, some complex stuff goes on. Clays might lose aluminum, gain boron, some silica might precipitate out. It's a slower process than the HF dissolution, more driven by thermodynamics.
So two processes happening at different speeds.
Yeah, the initial dissolution is fast, then the stabilization takes over, slower and steadier. They've even looked at this under a microscope, and you can see kaolinite platelets. They look like they're welded together to the quartz grains, maybe because of some borosilicate forming.
Wow.
And if you've got elite, that potassium-rich clay, well, fluoric acid forms a non-damaging potassium fluoboric acid.
Yeah.
Instead of that nasty potassium hexafluorosilicate you can get with mud acid. So that's a huge win in those formations.
Avoiding those precipitates is always good.
Absolutely. And the beauty of it is, during injection, fluoboric acid is like a weak HF solution that keeps getting replenished, so you're less likely to get those aluminum precipitates. And then during shut-in, those slower reactions keep going, releasing more HF, doing their thing. So it's like a two-pronged approach.
Interesting. Now, what about some of the other systems mentioned, like sequential mud acid?
Right, sequential mud acid. The idea is to inject alternating slugs of HF and ammonium fluoride. You're trying to create HF right there in the formation.
On the spot.
Yep. But there's some skepticism about whether it really works. The amount of HF you generate is probably pretty small. And it's very dependent on the clay type, how much cation exchange capacity it has. Might not work well on kaolinite, for example.
So limited effectiveness?
Possibly, yeah. Then there's alcoholic mud acid.
Okay.
That's just mud acid with alcohol added. Isopropanol or methanol, usually up to 50%. They mainly use it in low permeability gas zones. The alcohol slows down the reaction rate.
Why do you want to slow it down?
Well, in those tight formations, You want the acid to penetrate deeper before it spends. The alcohol helps with that. And as a bonus, it helps with cleanup afterwards, reduces surface tension, increases vapor pressure, so the gas flows better.
Makes sense. What about adding aluminum chloride to mud acid? That was another idea, right?
Yeah, the thinking was that the aluminum would bind to the fluoride, kind of like mimicking spent acid, slow down the reaction. But it hasn't really panned out in practice. Doesn't seem to retard clay dissolution much. The clay surface area is just too dominant. Plus, you risk getting those aluminum fluoride, or flualuminate, precipitates. Some tests have even shown that it penetrates less effectively than regular mud acid, and some field experience suggests it can actually increase scaling.
So more downsides than upsides.
Pretty much, yeah.
Then there's organic mud acid.
Organic mud acid, that's where you replace the strong HCl with weaker organic acids. Formic acid is common, maybe 9% with 3% HF. The goal is to slow down the HF spending because the overall acidity is lower. And this is good for high-temperature wells because the organic acids are less corrosive, less likely to form sludge at those temps.
So less harsh on the equipment.
Yeah, and on the formation potentially.
What about those self-generating mud acid systems?
Those are pretty interesting. The idea is to use organic esters that break down at high temperatures, releasing carboxylic acids. And those acids then react with ammonium fluoride to make HF. So it's like on-demand HF generation.
Activated by the formation temperature.
Exactly. They use different esters for different temperature ranges. Methylformate, ammonium salt of monochloroacetic acid, methyl acetate. Goal is to have the HFs generate slowly so it can penetrate deeper. But field tests haven't been that conclusive. And there's a big problem. A lot of precipitates can form in these low acidity systems. Things like ralstonite, flualuminates. They've tried adding citric acid to help, but it's still an issue.
So more research needed.
Yeah, it's promising, but not quite there yet. And there are other drawbacks. It's very temperature dependent, the esters are expensive and can be dangerous, and the solubility of the byproducts isn't great. The main benefit is less corrosion compared to regular HF.
Okay. And finally, there's buffer-regulated HF systems.
These are designed for high temperatures, up to 360 degrees Fahrenheit. They use organic acid buffers, things like formic acid and ammonium formate or acetic acid and ammonium acetate. The pH is higher, but they add ammonium fluoride to provide the HF. And they often do a pre-flush with just the buffer, no fluoride, to control corrosion.
So a two-stage approach.
Yeah. And for even higher temps, they increase the ammonium salt concentration to keep the pH in check. But the problem is they haven't been that successful at stimulating deep into the formation, except at lower temperatures. And they often cause precipitates near the wellbore because the acidity isn't strong enough in that area.
So similar drawbacks to the self-generating systems.
Pretty much. It seems like we're always fighting that balance between getting the acid to react where we want it to and preventing it from causing more problems.
It's a delicate dance. And, we've talked a lot about the chemistry, but the material makes a point that it's not just about the acid itself. There's more to damage removal than that.
Oh, absolutely. You can pick the best acid in the world, but if you don't know what you're dealing with, you're going to have a bad time.
So step one is identifying the contaminant.
Always. What's actually causing the blockage? Is it mineral scale? Is it organic gunk? Is it something else entirely? Because HCl, for example, it won't touch organic damage. You need solvents for that.
So different problem, different solution.
Exactly. No one-size-fits-all approach here. You got to evaluate the damage thoroughly, then pick the right tool for the job. And that tool, whatever it is, it's got to be compatible with the formation fluids and the rock mineralogy.
So you're saying even if the acid dissolves the damage, it might cause other problems down the line.
It happens all the time. You can get precipitates forming, emulsions, all sorts of nasty stuff. The material actually refers us back to a whole chapter on formation damage, just to emphasize how important this is.
It's fundamental.
It is. And the thing is, even if you do everything right, pick the perfect fluid, you can still run into problems downhole. Incompatibilities happen. You get precipitates forming, blocking those pores you just tried to clean, and the outcome, it can range from no big deal to wells completely plugged. They use core analysis, geochemical simulators, all sorts of fancy tools to try and predict this stuff, but it's not foolproof. You could still get surprised.
So it's a constant learning process.
It really is.
And preventing damage during the treatment, that's just as important as fixing the existing damage.
More important, even. And that's where understanding the formation properties comes in. Mineralogy, permeability, all that stuff.
So walk us through that. What are the key things to consider?
Okay, first, mineralogy. What's the rock actually made of? That tells you what kind of acid system, too.
All right. Welcome to another deep dive, everybody. We're ready to take all that info you've sent us and, well, distill it down. Pull out the good stuff, the stuff that really matters. Today, we're tackling ch19.pdf, all about fluid placement and pumping strategies.
Yeah.
Really the name of the game when we're talking about matrix stimulation treatments.
That's it, yeah.
Yeah.
You're basically asking, how do we get the most bang for our buck when we're trying to juice up production from a well, right? It's not just about pumping fluids down there. It's got to be strategic.
Exactly. And for everyone listening out there, this deep dive is for you, whether you're, wrestling with well optimization every day, maybe prepping for a crucial meeting, or just love learning about this stuff. We're going to break it down, make it clear, and hopefully leave you with some solid takeaways.
Because at its core, what we're dealing with here is a kind of self-sabotage when it comes to well stimulation.
Okay, self-sabotage. That's an interesting way to put it.
Well, think about it. Stimulation fluids, they're going to follow the path of least resistance, right? It's basic physics. And in a reservoir, that means they'll naturally flow into the zones that are already pretty permeable, kind of like, water flowing downhill. It goes where it's easiest.
So we end up over-treating the zones that are already doing okay and kind of neglecting the ones that could really use a boost, the tighter, more damaged zones.
Right. It's almost like, I don't know, putting a bandage on a scratch when you've got a broken arm.
Okay, yeah, I see the analogy. So the very act of trying to improve production can backfire if we're not careful about where those fluids are going. So let's get into the nitty-gritty. Why is precise fluid placement so crucial in the first place?
All right, so picture this. You've got a multi-layer reservoir, which is super common. And these layers, they all have different personalities, you could say. Some are like sponges, really good at soaking up fluids. Others are much tighter, more resistant. We call this injectivity contrast. And it can be caused by variations in the rock itself, its natural permeability, or how much damage a layer has experienced, maybe during drilling.
And it's not just separate layers, right? I mean, even within a single layer, you can have these gradients where permeability changes gradually.
Absolutely. And even the perforations themselves, those holes we make to connect the well to the formation, they can be damaged unevenly. So it gets pretty complex down there. The bottom line is that without some control, the zones that are already pretty good at taking fluids are going to hog the show, so to speak.
Yeah, that example in the PDF really drives this home. You've got that 3-layer reservoir, and one high injectivity layer, just 10% of the total zone, ends up taking over half the injected fluid.
Exactly. Yeah. And if you try to treat the entire interval without any kind of placement strategy, you end up needing way more fluid, which means more time and more cost. In their example, it was over double the volume.
Wow, that's a huge difference. So how do we wrestle back control and make sure the stimulation fluids are going where we want them to go? The PDF breaks down all these different techniques, both non-mechanical and mechanical. Let's start with the non-mechanical methods, so the ones that don't involve any fancy hardware. What are we talking about here?
Well, one common approach is to use what are called particulate diverters. Essentially, these are small particles ranging in size from tiny grains to larger particles that we mix in with the treatment fluid.
And these particles actually block off the high injectivity zones.
In a way, yeah. The idea is that they form a temporary low permeability barrier at the sand face, like a filter cake. So it's not a permanent blockage, but it slows down the flow in those zones and forces the fluids to go elsewhere, to those less permeable zones that need it most.
So it's like creating a detour on a busy road to redirect traffic. What are some other non-mechanical strategies?
Another one is using viscous fluid slugs. We basically inject slugs of fluid that are, well, thicker and more resistant to flow than the main treatment fluid. This temporarily reduces injectivity in those high flow zones.
So you just make the fluid thicker.
Well, it's a bit more nuanced than that. The type of viscous fluid you use matters. In simulations with those Newtonian fluids, the ones that have constant viscosity, it's not always as efficient as using particulate diverters. But there are more advanced gels, power law gels, whose viscosity actually changes with the flow rate, and those might offer some advantages.
Interesting. And what about using foam for diversion? I know that's used a lot in the oil field.
Foam can be a really effective diverting agent. We can either inject it as separate slugs or even mix it directly with the acid. The foam basically creates a temporary resistance to flow in the high permeability zones, diverting the treatment elsewhere.
I'm picturing, like trying to blow air through a straw that's got a sponge in it. It's going to be a lot harder than just blowing air through an empty straw.
Yeah, exactly. The trick with foam is getting the right formulation and injection parameters. Things like the type of surfactant, the ratio of gas to liquid, and even the presence of oil can affect how well it works.
Okay, so the big takeaway with these non-mechanical methods is that we're creating a temporary bottleneck in those high flow zones, forcing the treatment into those harder to treat areas. Let's move on to the mechanical methods, the ones that involve actual downhole tools. What kind of hardware are we talking about here?
Well, ball sealers are a classic example. These are small spheres, often coated with rubber, that are introduced into the well with the treatment fluids. As the fluids flow into the perforations, the balls can get carried along and actually seat in the perforations that are taking the most fluid, effectively blocking them off.
That sounds pretty straightforward. But I noticed the PDF mentions that they're not always effective in long intervals or wells with a ton of perforations. Why is that?
Yeah, so conventional ball sealers, they need a certain minimum flow rate per perforation to be effective. When you have a really long interval or lots and lots of perforations, it can be tough to maintain that flow rate at every single entry point. And gravity can also be a factor. They tend to settle at the bottom of the well bore in the rat hole, so they might miss upper perforations.
So gravity working against us again. But I see they also talk about buoyant ball sealers. Are those designed to overcome that problem?
Exactly. Buoyant ball sealers are designed to, well, float in the treatment fluid. So instead of settling down, they actually rise. This can make them more effective at sealing perforations higher up in the wellbore.
Ah, so clever. Turning a problem into a solution. What other tools do we have for mechanical diversion?
Packers are another go-to. They're basically inflatable devices that we can set in the wellbore to isolate specific zones. This lets us treat a certain interval without affecting the zones above or below, like having tiny little compartments downhole.
Sounds like it offers a lot of control.
It does, yeah. It's one of the most effective ways to really target a specific zone, but it usually requires coiled tubing or a rig to set and retrieve the packers.
And speaking of coiled tubing, the PDF mentions it as a vital tool, particularly for horizontal wells and long vertical zones. How does coiled tubing help with fluid placement?
Coiled tubing is essentially a really long, flexible pipe. We can run it downhole and deliver the acid or the diverting agents right where we want them. So we can treat long intervals, or in horizontal well, we can run it all the way to the toe and slowly pull it back as we inject, ensuring we're treating the entire lateral section.
Like having a tiny little hose you can snake through the well.
Right. And the PDF also mentions a technique specific to carbonate formations using gelled acid. How does that work for fluid placement?
Right, so with gelled acid, the viscosity changes as the acid reacts with the rock as it spins. So in zones where a lot of acid has already reacted, the gel becomes thinner, reducing the injectivity there. This naturally diverts the fresh acid to the less treated zones. So the acid itself is helping to direct the flow as it does its job. That's pretty neat. Now, there was a study mentioned that compared different diversion methods. I think it was by Hill and Rawson, and they talked about something called, what was it, MAPI?
PDR stands for maximum pressure differential and injection rate. It's a bit of a different philosophy. Basically, you pump at the highest rate the formation can handle without fracturing, but you don't use any specific diverting agents.
So it's more about brute force than finesse.
In a way, yeah. Proponents of MAPDIR argue that it reduces the overall treatment time and can be effective in certain scenarios where you don't have huge differences in permeability between the zones.
But it doesn't really address the fundamental problem of uneven injectivity, does it?
Well, that's the debate. Some studies suggest that in carbonates, even if you don't initially get even distribution, the continued injection at a high rate can eventually lead to improved injectivity across the entire interval as those tighter zones slowly open up. But it's definitely not a one-size-fits-all solution.
Right. It sounds like it has its limitations. And that study by Hill and Rawson seemed to indicate that continuous injection of particulate diverters was the most efficient in terms of the overall volume of fluid you need.
Yeah, their simulations definitely pointed in that direction.
Yeah.
But again, the best approach really depends on the specifics of the reservoir and the well. There's no magic bullet here.
Okay, so how do you actually choose which diversion method to use? What factors do you have to consider?
Well, it's a multifaceted decision, for sure.
Hmm.
For particulate diverters, you've got to think about the reservoir's permeability, the size of those pore throats, and the compatibility with the fluids in the wellbore and with the acid.
Right, you don't want the diverter to dissolve before it does its job or react with the acid and create some nasty gunk downhole.
Exactly. And the type of well completion matters too. If you've got a gravel pack, you don't want to use large particles that could plug up the screen. Foam is often a good choice there.
And foam can also be good for selectively plugging water zones in an oil well, right?
Yeah, because the oil can actually break down certain types of foam, so you can target the acid towards those oil-producing zones.
Interesting. It's like each diversion method has its own special talent. And for those really long intervals or situations where you need pinpoint accuracy, packers and coiled tubing are the way to go, even though they can be more expensive.
Right. It's all about choosing the right tool for the job. Now, another aspect we need to think about is the relationship between fluid placement and the injection rate. It seems like there's a bit of a balancing act there.
Yeah, the PDF mentions that most placement techniques tend to reduce the overall injection rate, which can impact the efficiency of the acidizing reaction.
It's true. And with sandstone acidizing, you generally want a higher injection rate to prevent those secondary reactions that can form damaging precipitates and to ensure the acid penetrates deep into the formation. But some research suggests that there might be an optimal rate based on the reaction kinetics. You want it to react fast enough to dissolve the damage, but not so fast that it's all spent right at the wellbore face. And for carbonates, a high injection rate is absolutely crucial for creating those wormholes.
So finding that sweet spot between effective placement and the optimal injection rate is key. Now, let's dig a bit deeper into those chemical diverters. The idea of using materials that are insoluble in acid but then dissolve in water or hydrocarbons later on is pretty ingenious.
It is, and it's a huge improvement over the older methods of using viscous polymer slugs, which were often difficult to clean up. Chemical diverters are designed to form that temporary low permeability cake at the sand face, just like the particulate diverters, but then they dissolve away cleanly after the treatment.
And the evolution of these chemical diverters is quite a story, starting with simple things like soap solutions and eventually leading to the more sophisticated materials we have today.
Oh yeah. Early on, they even tried creating solid precipitates downhole to block the flow, which could easily cause permanent damage. Rock salt was a step forward because it's partially soluble in acid. But the real breakthrough came with those fully soluble materials, like benzoic acid for water injection wells and those hydrocarbon resins for oil wells.
So what makes a chemical diverting agent truly effective? What should we be looking for?
Both its physical and chemical properties are important. You want the filter cake it forms to be really tight, with low permeability, and you want minimal invasion into the formation so it cleans up easily. That means finding the right particle size is crucial. Chemically, it needs to be compatible with the other treatment fluids and not react with the acid. And of course, it's got to dissolve completely after the treatment.
The PDF classifies them by particle size into bridging and plugging agents and those finer particulate diverters. When would you choose one over the other?
Bridging agents, with their larger particle sizes, they're typically used in carbonates with natural fractures or vugs, larger openings. They basically bridge across those openings and start to create a seal. But the cakes they form can sometimes have higher permeability, so they might not be as effective in those super high perm zones. Particulate diverters, on the other hand, have much smaller particles, perfect for creating a tighter seal in the matrix rock. And of course, you choose water-soluble types for injection wells and oil-soluble ones for production wells.
Got it. So bigger particles for bigger features, smaller particles for a tighter matrix seal. Makes sense. But I'm guessing things don't always go perfectly smoothly downhole. What are some of the common problems you can run into with diverters?
Well, one issue is decantation, where those heavier bridging agents can settle out before they reach the formation. Luckily, it's less of a problem with those finer diverters. Solubility can also be tricky. You don't want those water-soluble diverters dissolving in the acid before they get to where they're needed. And if the particle size is off, you can have problems. Too large, and they might not create enough resistance. Too small, and they might migrate too deep into the formation and make cleanup difficult.
Right. It's all about finding that Goldilocks zone. And chemical compatibility is a big one, too. Certain combinations can lead to flocculation, where the particles clump together, or even create damaging precipitates.
Exactly. Careful lab testing is essential. They even have specialized equipment, like Crow's equipment, to test the efficiency of different diverters in core samples. And sophisticated well models are used to predict how the flow will distribute during the treatment.
It's amazing how they can take those lab measurements and turn them into models to guide the design of these treatments. Now, let's talk about foam diversion. The physics of how foam behaves in porous media is, well, pretty mind-boggling.
It is fascinating, and our understanding of foam diversion in the near wellbore region has benefited a lot from all the research on using foam for enhanced oil recovery. But it's important to remember that the flow rates and patterns are quite different during stimulation.
So what's so special about foam? It's not just soap suds, right?
Right. In those tiny pore spaces, foam bubbles, which are actually larger than the pores themselves, they get squeezed and elongated, forming these thin films called lamellae. And the behavior of the foam is mostly controlled by the capillary forces acting on these lamellae.
And the key is that foam reduces the mobility of gas in the pore space, which in turn redirects the liquid acid.
Exactly. Foam doesn't really change how easily the water itself can flow. It just reduces the relative permeability to the liquid phase by taking up more space with those gas bubbles. And those capillary forces can actually trap a good portion of the gas even as the rest of the foam is flowing.
The PDF talked about two simplified regimes of foam behavior. One where the bubble size is mainly determined by lamellae destruction, and another where capillary trapping dominates. Can you explain those a bit more?
Sure. In that first regime, where lamellae destruction is the main thing controlling bubble size, the foam can act a lot like a low-mobility Newtonian fluid. And interestingly, under these conditions, stronger foams tend to form in higher permeability rock. This is great for diversion because it means those high perm zones get blocked more effectively. The other regime is dominated by capillary trapping. In some cases, the pressure drop across the foam or the pressure you need to inject the following liquid can become nearly independent of the flow rate. This suggests that as you try to push more fluid, you're just mobilizing some of that trapped gas.
So foam behavior is definitely not simple. It's influenced by the foam quality, the injection rate, and the rock permeability, just to name a few factors.
Absolutely. And foam tends to be strongest, meaning it offers the most resistance to flow when the gas content is somewhere between 70% and 90%. At very high flow rates, foam can become non-Newtonian, meaning the relationship between the pressure and flow rate isn't linear. And oil can actually weaken or destroy foam, especially in oil-wet rock. This can be a problem, but we can also use to our advantage to selectively treat oil zones.
So what happens when you inject acid after a foam stage? Does all that trapped gas just block the acid?
Well, experiments show that the gas trapping isn't perfect. The pressure needed to push the liquid through tends to decline over time, partly due to gas mobilization and maybe some gas dissolution. But the key point is that the pressure drop after foam injection often doesn't depend that much on how fast you injected the foam or how fast you're injecting the acid. It seems to be more controlled by how easily that trapped gas can move. And how fast the pressure declines after foam injection might be just as important as the final steady pressure, especially in the field where injection times are often limited.
The PDF also talked about how the rate at which the foam moves through the formation is limited by how fast the surfactant can travel, because it likes to stick to the rock. And it moves faster in high-porm rock and if you use a surfactant pre-flush.
Exactly. A pre-flush helps to coat the rock surface, so less of the surfactant in the foam gets absorbed, allowing the foam to propagate further. And in carbonates, foam can actually influence the way wormholes form, leading to longer, more efficient channels. It can even plug existing wormholes, forcing the acid to create new pathways.
Foam seems like a really versatile tool, but it's clear you need to understand the nuances of how it behaves to use it effectively. They even have all these different mathematical models to predict foam behavior, ranging from really complex ones to simpler approaches.
Yes, choosing the right surfactant, the right foam quality, and the right injection strategy is crucial. And field experience, along with careful monitoring during the treatment, are essential.
Hmm.
All right, let's circle back to ball sealers for a bit. We talked about the difference between buoyant and conventional types, but what are some of the practical things to consider when you're actually planning to use them?
Yeah, like how do you pick the right ball for the job?
Well, conventional ball sealers, they need a good amount of flow to carry them down and seat them properly. And their effectiveness depends on the shape of the perforations. Buoyant ball sealers can overcome some of those limitations, but you have to make sure their density is just right. They need to be light enough to rise, but heavy enough to be carried down initially.
Sounds like a bit of a balancing act. And what about those other mechanical tools we touched on earlier, the ones that were used before coiled tubing and packers became so common?
Yeah, there's been a whole evolution of tools. They had these interface locator tools that tried to pinpoint the boundaries between different fluids to target specific zones. Hydraulically inflatable packers have been around for ages, allowing you to isolate multiple intervals in a single trip. Frac baffles were another attempt at selective treatment, but they were tricky to place accurately. And then you have retrievable packers, especially the tension set kind, which are well suited for matrix acidizing.
So lots of clever ideas over the years, all aimed at solving that same problem of getting the fluids where they need to go. And finally, let's talk about horizontal wells. They pose some unique challenges for fluid placement, right?
Big time. I mean, the length of the producing interval in a horizontal well can be just massive compared to a vertical well. And there are often limitations on how much acid you can pump per foot of well bore because of corrosion inhibitor limits and time constraints. So if you just pump acid down the well without any diversion, you might only treat a small section near the heel.
So diversion techniques are even more critical in horizontal wells.
Generally speaking, yes. Production logs after non-diverted acid treatments in horizontal wells often show that most of the production is coming from just a small area near the heel. Designing the treatment involves carefully considering how much acid you can use and often adjusting the injection volumes based on how much damage you expect along the wellbore. And sometimes selectively acidizing only certain sections can actually improve the overall productivity, although usually treating the entire wellbore gives the best economic results.
And I'm guessing ball sealers aren't really an option in those open hole or slotted liner completions that are common in horizontal wells?
Right. Conventional ball sealers just aren't practical in those types of completions. So what are the go-to methods in horizontals?
Well, coiled tubing is really the workhorse. A common technique is to run it all the way to the toe and then slowly pull it back as you inject, controlling the placement with the retrieval rate. And diverter stages, either foam or particulate diverters, are usually pumped periodically during this process. Another technique is to pump an inert fluid down the annulus to create back pressure, forcing the acid out into the formation. And there are also adaptations of that MAPDI method, where you spot acid with coiled tubing and then pump at a high rate. But coiled tubing really is the key for those long horizontals.
Well, wow, we've covered a lot of ground today. This has been a truly deep dive into the world of fluid placement and pumping strategies for matrix stimulation treatments. It's been great having you on to guide us through all the intricacies.
My pleasure. It's been a great discussion. So for all of you listening out there, we hope this has demystified some of the complexities of matrix stimulation. We've talked about the crucial importance of getting those fluids to the right places, the different techniques available, both mechanical and non-mechanical, the factors you have to consider when choosing a method, and the particular challenges of horizontal wells.
The big takeaway, I think, is that it's not just about pumping more fluid. It's about pumping smarter.
Exactly. And for our listeners who are eager to keep learning, what questions do you have for us? What aspects of fluid placement are you particularly curious about? This is a field that's constantly evolving, with new technologies and techniques emerging all the time. And hey, maybe check out that chapter 17 in your source material on self-diverting acid. Sounds like it could be a whole other deep dive.
And here's something to ponder as you continue to explore this fascinating topic. With a growing emphasis on maximizing production from existing wells and minimizing our environmental footprint, how might advancements in areas like real-time downhole monitoring and adaptive stimulation techniques change the game even further? Could we one day have systems that are constantly adjusting the fluid placement based on real-time feedback from the reservoir? The future of well stimulation is full of exciting possibilities.
Lots to think about, for sure. Thanks again for joining us on this deep dive, everyone. We'll catch you on the next one.
Until next time. All right, welcome back to the deep dive. Today, we're diving into something that, on the surface might seem pretty straightforward, but as we dig deeper, we'll see it gets pretty tricky. And that's how we know if a matrix stimulation treatment has actually worked. Like, did it do what we hoped it would do down there in the reservoir?
Yeah, it's a great question and a surprisingly complex one, especially when you compare it to something like hydraulic fracturing, right? With fracking, you've often got these pretty extensive pre- and post-treatment tests to tell you what's changed. But with matrix stimulations, the cost of that kind of testing often just doesn't make sense. So we got to get creative.
Exactly. I mean, every operator wants to see those productivity and injectivity numbers go up after a treatment. But just like our sources have been saying, you can't just take those top-line results at face value. There's a lot more happening downhole than those surface measurements might suggest.
Absolutely. And that's where understanding skin effect becomes really crucial. Think of it this way, like imagine you've got a filter on your kitchen faucet, right? But over time, it gets clogged with gunk and it becomes harder and harder to get water through it. The skin effect is kind of like that clogging around your wellbore. A positive skin means it's more difficult for fluids to flow in or out. Now, matrix treatments are designed to, in a sense, clean that filter, chemically dissolve that damage that's been caused by things like drilling or completion fluids.
So it's like unclogging the well, right?
Exactly. But here's the thing. A well test can tell you the total skin effect, but it doesn't differentiate between damage-related skin and mechanical issues like, say, poorly placed or underperforming perforations. Matrix treatments are specifically targeting that damage-related component, and we want to see that portion of the skin decrease. And of course, the economic side of things always comes into play. We want to use the least amount of chemicals and pumping time to get the job done effectively. No one wants to overspend on a treatment.
Right. Makes sense. So this need to know what's happening downhole in real time as the treatment's actually going on has led to some pretty innovative thinking, hasn't it? Like, can we get a live feed of that filter being cleaned?
Oh, absolutely. And that's where the work of folks like McLeod and Coulter, Pacaloni, Prouvost and Economides, Behenna, Hill, and Zhu, these are some of the pioneers who've really pushed the boundaries of real-time skin effect monitoring during stimulation treatments. It's a seriously cool challenge.
It's like trying to get a live ultrasound of the wellbore while it's being worked on, right?
Yeah, exactly. But the problem is that getting direct measurements downhole, especially with all those harsh chemicals swirling around, it's incredibly tough on instruments. And that's what makes these alternative approaches so clever.
They had to think outside the box, so to speak.
They did. Instead of relying on those direct downhole measurements, a lot of these techniques use what we can easily measure at the surface, things like pressure and flow rate at the wellhead. And then by combining those surface measurements with sophisticated mathematical models, we can start to infer what's happening down in the reservoir.
It's like detective work, right?
Yeah.
Piecing together clues to figure out the bigger picture. And sometimes you get other clues, too, like monitoring the pressure in the annulus, what's called backside pressure, can give you hints about fluid movement and potential restrictions. Or even using sound waves, like with ecometers, to measure fluid levels in the wellbore. Okay, so let's get into the specifics of some of these techniques. We got McLeod and Coulter. They came up with this approach where they essentially break the treatment down into a bunch of mini well tests, right?
Yeah, you got it. They looked at each individual injection stage or shut-in period during the treatment as if it were its own little short well test. And they applied the classic pressure transient analysis methods, the diffusivity equations, superposition principle, all that good stuff, to try to understand how the pressure was behaving during those short periods.
So they were trying to analyze how pressure built up or declined over time to give them insights into what was happening in the reservoir near the wellbore.
Exactly. And although they often presented their results in terms of things like permeability in the damaged and undamaged zones, and how far that damage extended radially outward from the wellbore, their ultimate goal was always to figure out that trippy skin effect.
So by carefully examining those pressure changes, they could potentially get a handle on the extent of the damage and how permeable the formation was in those different zones.
Right. But this approach, while pioneering, had some pretty significant limitations, didn't it?
Yeah, it kind of reminds me of trying to take a picture of a race car with a slow shutter speed. You might get a blurry image that doesn't quite capture the action.
That's a great analogy. See, the whole analysis relied on this assumption that the skin effect was staying constant during each of those mini tests. But that's just not realistic when you've got reactive fluids like acids actively working to dissolve the damage, right? The skin is constantly changing as the treatment progresses. Ideally, to make this method truly accurate, you'd have to stop the treatment every time you wanted to take a measurement and inject a slug of inert fluid. But that's just not practical and can really disrupt the treatment flow.
It's like pausing the acid job every few minutes to take a measurement. Not exactly ideal.
Nope. And the other big drawback was that it only gave you those snapshot measurements, usually before the treatment started and then again after it was finished. So you missed out on seeing how the skin was evolving in real time as the treatment went on. No real-time feedback meant no opportunity to adjust the treatment on the fly if things weren't going as planned.
Okay, makes sense. So then Pacaloni came along and tried to tackle this real-time monitoring challenge. And his method focused on using instantaneous pressure and flow rate measurements to try to calculate the skin effect in the moment, right?
Yeah, that's right. His approach was based on this idea of steady-state radial flow. Now, steady state means that the pressure distribution in the reservoir isn't changing much with time. And he cleverly incorporated this concept of an acid bank, essentially a zone of acid around the wellbore, and used an effective wellbore radius that took into account the skin effect. By assuming that the permeability thickness of the reservoir, that Kth value, was known, he could predict what the bottom hole pressure should be for different values of skin effect at a given injection rate.
So they would take that pressure measurement from the wellhead, estimate what the pressure was actually doing downhole at the reservoir level, and then see which theoretical skin effect value best matched that actual measurement.
Exactly. And Pacaloni also came up with this concept of a damage ratio, which is basically a ratio of how productive a well could be if there were no skin damage, compared to how productive it actually is with the existing skin. Figure 20:1 in our materials shows these damage ratio curves plotted against wellhead pressure for different injection rates. The idea is that as acid is injected and the skin effect hopefully decreases, you'd see that wellhead pressure move across those curves, giving you an indication of how the treatment is progressing.
I see those dashed lines in figure 20:1 showing the initial and final pumping conditions. So the idea is you track that pressure movement and know if you're heading in the right direction toward a successful stimulation.
Yeah, that's it. But here's the catch. Pacchilone's method, while innovative, relied heavily on that assumption of steady-state flow. And in reality, steady-state flow is rarely achieved, especially during relatively short-duration matrix treatments. Transient flow effects, where the pressure is changing significantly with both time and distance from the wellbore, dominate the picture.
And in fact, equation 20:4 in our materials shows that the estimated time to reach pseudo-steady state, which is kind of an approximation of steady state in a typical oil reservoir, can be more than 50 hours. That's way longer than a typical matrix acidizing job.
Exactly. And figure 20:2 really drives that point home, visually comparing how bottom hole pressure evolves according to both steady state and transient models. The two curves are significantly different.
And equation 20:5 points out that this discrepancy can be mistakenly interpreted as an increase in skin effect. So you might think you're dealing with more damage than you actually are, leading to unnecessary acid pumping.
Exactly. You might end up overtreating the well, trying to remove a skin effect that's really just an artifact of those transient flow dynamics, not actual damage. And that, of course, can get expensive and doesn't really benefit you in terms of improving the wall's performance.
Okay, so Pacchione gave us real-time monitoring, but with that steady-state assumption, it could be a bit misleading. So then Provost and Economides enter the scene, and they try to tackle those pesky transient effects head-on, right?
You got it. Their approach was to continuously calculate the skin effect throughout the treatment by comparing the actual pressure they were measuring in the well to the pressure predicted by a simulation. But here's the key difference. Their simulation incorporates the transient response of the reservoir based on the actual injection rates used during the treatment. As the treatment goes on, the difference between the measured and simulated pressures gets smaller and smaller, and they attribute that to the skin effect being reduced as the damage is dissolved.
So it's like they're constantly updating their prediction based on what's actually happening downhole, accounting for those changing pressures over time.
Precisely. But to do that accurately, you need to know a good bit about the reservoir before you even start. Things like its permeability, porosity, the properties of the fluids. It contains all those things that influence how pressure behaves.
Right, so it's not just a plug-and-play solution. You need some good upfront data about the reservoir.
Absolutely. And our materials in section 20 to 4.2 suggest a specific procedure for getting those crucial estimates. It involves a pre-treatment injection and pressure fall-off test using the reservoir's native fluids, the fluids that are already in the formation.
Right, so you essentially inject some of the reservoir fluid back into the formation at a controlled rate, then stop the injection before any treatment fluids get involved, and carefully record how the pressure declines.
Exactly. And by analyzing that fall-off data, you can get a decent handle on the reservoir model, the permeability thickness, that KH value, and a crucial initial value for the skin effect before the treatment even starts.
And since you're using the reservoir's own fluids, you avoid any complications from those reactive treatment chemicals. So then during the actual treatment, they take that initial skin value and plug it into their simulation, along with the recorded injection rates.
Right. And the beauty of it is that at any point during the treatment, they can use equation 20:6 to calculate the skin effect based on the difference between the simulated pressure, which assumes that initial skin, and the actual pressure being measured in the well. And this equation also accounts for things like the injection rate, the formation of volume factor of the fluids, and their viscosity.
So any difference between what the simulation predicts and what they're actually seeing in the well is attributed to the skin effect changing as the treatment progresses.
Yeah.
Pretty ingenious.
It is, and unlike Pacchilone's method, this one embraces those transient effects, which, as we know, are a reality in these treatments.
It's like they've finally figured out how to take a clear picture of that race car.
Exactly. And even in trickier situations, like layered reservoirs where that pre-treatment test might only give you an average skin effect across all the layers, you can still learn a lot by tracking how that average skin changes over time.
Right. If you see that skin effect curve flattening out at a non-zero value, that might tell you that the treatment isn't reaching all the damaged zones, or that maybe one zone is cleaned up while others still need attention.
Exactly. And sidebar 20A in our materials shows a nice example of this method in action. They even compare it directly to Pacchioloni's technique, and you can really see how Pacchioloni tends to overestimate the skin effect, especially when the injection rate is reduced.
Yeah, figure 20A3 really highlights that. Get this unrealistic jump in the skin effect calculated by Pacchioloni, while Provost and Economides, by accounting for those transients, show a much smoother, more realistic trend. Okay, so Provost and Economides gave us a way to deal with those transient effects. And then Behana came along and said, hold on, we're also using these diverting agents. We got to account for those too, right?
That's right. Diverting agents are like traffic cops, helping to direct those treatment fluids to different parts of the wellbore. But they also create a temporary restriction to flow. It's like adding another filter on.
A layer of complexity, right?
No, exactly. And Behana realized that this additional restriction could be misinterpreted as part of the actual formation damage. So his method essentially subtracts the pressure drop caused by the diverting agent from the overall bottom hole pressure before calculating the skin effect.
So you're isolating the pressure response that's truly due to the formation damage being removed, not just the temporary blockage from the diverter.
Precisely. And figure 22.3 in our materials shows how this correction can be applied in practice. Behana also went a step further and proposed looking at the derivative of the skin effect with respect to time.
The rate of change, right?
Exactly. Plotting this derivative helps to highlight those moments when the skin effect is changing most rapidly, giving you a clear indication of when the most significant damage removal is happening.
It's like seeing not just how much damage is being removed, but also how quickly it's being removed.
Exactly. And it also helps smooth out any noisy data you might have and gives you a quantitative measure of that damage removal rate. A steeper slope on that derivative curve means faster cleanup. Pretty neat, huh?
Yeah, very cool. So then we've got the inverse injectivity diagnostic plot, developed by Hill and Zhu. And this one also aims to incorporate those transient flow effects, but maybe in a more straightforward way.
Yeah, you could say that. They basically derived an equation 20-7 in our materials, that relates a bunch of key parameters: the initial reservoir pressure, the flowing pressure at the bottom of the well, the injection rate, and a superposition time function, which takes into account the entire history of injection rates.
So that superposition time function is how they capture those transient flow effects.
You got it. They then define these simplified terms, unprime and b'prime, which incorporate the reservoir properties and the skin effect. And the heart of their method is to create a plot of inverse injectivity, which is just the change in pressure divided by the injection rate against that superposition time function. If the reservoir parameters and the skin effect stayed constant, this plot should give you a straight line, right?
Okay, I'm following.
And the slope and intercept of that line are directly related to those reservoir properties and the skin effect. So before the treatment even starts, they generate a bunch of these theoretical straight lines, each representing a different possible skin effect value.
So you've got this library of lines representing different skin scenarios.
Exactly. And then as the treatment progresses and the skin effect changes, the real-time data points you're collecting will shift between those pre-calculated lines. By watching how those data points move, you can track the progress of the stimulation.
And you can see that illustrated in figure 20b1, another one of those job control graphs. It's like following a dot on a map as the treatment progresses.
That's a great way to put it. And the beauty of this method is that it implicitly accounts for those transient flow effects without getting too bogged down in complex mathematics. It's a very practical approach.
It's fascinating how each of these techniques is built upon the previous ones, trying to overcome limitations and refine the accuracy of real-time monitoring. But it's clear that this is not a simple problem to solve.
No, not at all. As our materials highlight, it's not just the damage removal that's influencing the bottom hole pressure during a treatment. You've got the reservoir's natural response to those changing injection rates, different fluid viscosities being introduced, those temporary skin effects from the diverting agents, and then a whole host of other factors that can complicate the picture.
It's like trying to solve a multivariable equation where some of the variables are constantly changing.
Right. And so the ongoing challenge is to tease apart those different influences and isolate the pressure response that's specifically due to the damage being removed by the treatment. That's the signal we're after amidst all that noise.
Makes sense. And that's where those diagnostic tests performed during the treatment itself become really valuable, right? Our materials in figure 20-4 actually outline a kind of hierarchy of interpretations, starting with basic well diagnostics.
Yeah, that's a good way to think about it. So at that first level, even before you start the stimulation, you can run a step rate test or an injectivity test using a non-reactive fluid. This essentially helps you determine if the well is even a good candidate for matrix stimulation in the first place.
Right, you're trying to rule out other potential causes for the well's poor performance before you jump into a potentially expensive treatment.
Exactly. And the way you do this is by injecting at a series of increasing rates below the fracturing pressure and carefully monitoring the pressure response. By analyzing that pressure data, you can calculate an apparent skin effect at each constant rate.
And if that calculated skin effect stays fairly constant across those different rates, it tells you that your initial assumptions about the reservoir's permeability thickness are probably pretty solid.
And more importantly, if that initial skin effect is already zero or even negative, it's a big red flag that a stimulation treatment might not be necessary.
It's like the well is telling you, hey, I'm actually not clogged. The problem lies elsewhere.
Precisely. But if the well diagnostics suggest that stimulation is warranted, then you can move up that interpretive ladder to the treatment optimization level. Here, the focus is on analyzing the shape and duration of the pressure response during the actual injection of those treatment fluids.
Right, and the example shown in Figure 20-5, that acidizing response curve from a water injection well, is a great illustration of that.
Yeah, that one's a classic. Just by looking at how the pressure changed as they injected different fluids, the operators were able to deduce that the likely culprit was carbonate scale or iron oxide, which would be dissolved by hydrochloric acid but not mud acid. And they could even estimate that most of that damage was removed with a relatively small volume of HCl. They didn't need to overtreat.
They were essentially watching the well respond to the treatment in real time and making adjustments as needed.
Exactly. And they even used information about the reservoir's porosity and the effective treatment height to estimate the radial extent of that damage. Plus, the post-treatment spinner surveys showed that only about a third of the perforated interval had actually received treatment, highlighting the potential need for better diversion techniques in the future.
Right, it's not just about pumping acid, it's about making sure it gets to the right places.
Absolutely. And Sidebar 20C brings up another really important point, which is that sometimes declining production might look like it's caused by near wellbore damage, but the real culprit could be something completely different, like a decrease in the overall reservoir pressure.
Right, it might not be a clogged filter at all, but rather a decrease in the water pressure feeding the whole system.
Exactly. And that example from the two-phase reservoir shows how that dilemma can play out. Even though a recent well test showed a skin effect of zero, production had still dropped significantly. But by analyzing IPR curves, those inflow performance relationships, and VLP curves, the vertical lift performance curves, as shown in Figure 20C1, they could demonstrate that the same production decline could be caused by either a moderate increase in skin effect or a significant drop in reservoir pressure.
So you really need to do your due diligence and rule out other possibilities before assuming that a stimulation treatment is the answer.
Absolutely. Don't just jump into an expensive treatment without understanding the root cause of the problem. Now, once the treatment is done, we can also use a variety of post-treatment evaluation techniques to assess its effectiveness. Besides those real-time methods we've been discussing, we can also run pressure buildup tests before and after the treatment, do some production logging, and even analyze the fluids that return to the surface.
Return fluid analysis. It's like getting a lab report from the well after surgery.
Kind of, yeah. By looking at the concentrations of different ions in those return fluids, you can get insights into what the acid actually reacted with downhole. Table 22, for example, shows the measured aluminum and silicon concentrations in the return fluids from two wells. And when they compared those measurements to the theoretical concentrations based on the acid composition, they found evidence of significant secondary Clay reaction precipitation.
So the well was basically saying, hey, that particular acid mix wasn't ideal. We got some unintended side reactions down here.
Exactly. And that finding led to a recommendation to use a different acid ratio in future treatments, one that would minimize those unwanted precipitation reactions. It's like fine-tuning the recipe based on feedback from the well itself. And tracer surveys can also be really helpful. They involve injecting small amounts of radioactive tracer materials along with the treatment fluids. This allows you to track where those fluids actually travel within the formation.
It's like putting a GPS tracker on the acid.
Exactly. And Figure 20-6 shows a cool example of this. They compared two treatments in the same limestone well. The first treatment used rock salt as a diverting agent, but the tracer showed that most of the fluid just ended up in the top zone. The diversion wasn't effective. But in the second treatment, they used mechanical isolation with tubing and a packer to isolate the upper zone, and then used rock salt between acid stages in the lower zone. The tracer showed much better fluid placement this time, although they did see some potential leakage around the packer.
So there's always room for improvement, right? Even with these advanced techniques, we're still learning and refining our approaches.
Absolutely. And figure 20 to 7 shows those post-production curves for that second treatment, the one with the improved fluid placement, giving us a glimpse into the ultimate impact on the well's performance. So it's clear that evaluating the effectiveness of matrix stimulation treatments is a complex, multifaceted endeavor. It's a balance between the cost of testing and the need to know if the treatment actually worked. But the advancements in real-time skin effect monitoring, especially those methods that embrace those transient flow effects and utilize reservoir models, have given us powerful new tools for assessing these treatments.
It's like we've gone from blurry pictures to high-definition video.
Exactly. And when you combine those real-time techniques with the array of post-treatment evaluation methods we've discussed, those build-up tests, the logging, the tracer surveys, the fluid analysis, comparing IPR curves, you can really start to paint a detailed picture of what happened downhole.
You're gathering all these different pieces of evidence to solve the puzzle of stimulation effectiveness.
Precisely. And as we wrap up this deep dive, it leaves us with a thought-provoking question for you, our listener. How will this continuous evolution of real-time monitoring and post-treatment analysis shape the future of smart well interventions? How can we leverage this data to tailor stimulation strategies to the unique characteristics of each individual well? It's a fascinating area ripe for innovation, and the potential for optimizing well performance and resource management is immense.